In this episode, the tallest bridge on Earth.
The deck is about 150 meters above the Plateau de France.
Crossing one of Europe's deepest valleys.
With a pier and the tower above, it's higher than the Eiffel Tower.
And the pioneering historic innovations.
All right, now this is what I'm talking about.
Today, the Strömsund Bridge is a real landmark breakthrough in the world of engineering.
That made the impossible possible. Nestled in the southern corner of the Massif Central in France is the tranquil medieval town of Millau. However, for decades, every summer, that tranquility was shattered. Lying directly in the path of the fastest and busiest transport link between Paris and the Mediterranean coast, this historic town became a traffic nightmare.
Millau is not at all adapted to the motorway traffic. When the traffic from the tourists coming back from vacation in July, the other one coming down in August, it could be necessary to have 3 hours to cross Millau.
Finding a solution would become engineer Millau Viadoc's biggest challenge. To bypass the town and unblock this vital route across Europe, he would need to achieve what was previously thought impossible: build a road across the gargantuan Tarn Valley.
The first difficult point was to select where to cross the valley, because there is almost 300 meters between the plateau and the deep part of the valley. There have been big debates at the time, many alternatives were analyzed. Finally, it was decided to fly over the valley.
To achieve this extraordinary feat, engineers created a masterpiece. The Millau Viaduct. Spanning a staggering 2.5 kilometers and towering 343 meters above ground, it is the tallest bridge on the planet. Touching the Tarn Valley floor only 7 times, the slender concrete piers support a 36,000-ton aerodynamic steel deck, held audaciously in place by a single row of 154 super-strength cable stays. Completed in 2004, this magnificent sky bridge has pushed modern architecture and engineering to its limits.
Many thought it was impossible to build that bridge, and there have been many controversies on the bridge type.
So much controversy that in 1993, an international competition was launched to find the solution. And the prize was awarded to architect Lord Norman Foster, alongside engineer Millau Viaduct.
Each new bridge is a new challenge, a new project, and must be designed very specifically. In this case, we had a very important series of problems to solve.
Not only did the bridge have to span one of Europe's deepest and widest valleys, but rest on an uneven valley floor and be subjected to extreme wind forces at deck height. But perhaps the biggest challenge of all, it had to be completed in less than 4 years and built to last.
What is very important is to give the durability to the bridge. The contract specifies that the lifetime of the bridge is 125 years, so it's something very important.
So how do you create such a colossal bridge of extreme strength in record time. Engineers first needed to choose the right materials, a task that would not have been possible without the great innovators of the past. Man's earliest building materials were sourced from nature. Neanderthals built shelters from the bones and tusks of woolly mammoths, usually when the mammoth had finished with them. For thousands of years, Mongolian nomads have used sheep wool to line the walls of their yurts. Although not everyone's happy about it. From the time of ancient civilizations, many houses have been built with straw and clay bricks, reinforced with a touch of animal dung, which works perfectly, if you're standing in the right place. But to create a truly enduring structure, engineers at Millau would look to the work of a pioneering British civil engineer a quarter of a millennia earlier. Professor Luke Bisbee is taking a trip into the English Channel, one of the world's busiest shipping lanes, to find out more.
I'm heading out to the Eddystone, one of the most treacherous rocks in the English Channel. And it's a place that arguably marks one of the most important moments in civil engineering history. Today sits a 50-meter tall lighthouse designed by James Douglas in 1882. Amazingly, this is the fourth lighthouse that stood in this spot.
"22 kilometers from the busy port of Plymouth, over the centuries, the Eddystone Rock has sunk countless ships. As maritime trade increased in the 17th century, it was ordered that a beacon of light be built on top.
A building that could withstand the elements out here, the pounding of the waves day after day and the wind and the rain, requires a real engineering achievement.
In 1696, it was Henry Winstanley who completed the world's first offshore lighthouse, a 25-meter wooden tower. But 7 years later, it was obliterated by a storm. Its replacement survived 47 years, until being destroyed in a fire.
And if a lighthouse was going to last any substantial amount of time out here, a new engineering solution was needed.
In 1756, this seemingly impossible challenge fell to engineer John Smeaton. He believed that the sea must give way to the building, and decided to build a lighthouse made of stone. But it was how he joined the stones together that was truly revolutionary, and earned him the title the father of civil engineering.
Smeaton's original lighthouse stood on this spot for over 120 years, and in fact we can still see the bottom half of it as that stump of a lighthouse over there.
The structure had been so strong, it was only cracks in the rocks that it sat on that forced engineers to dismantle the lighthouse, and later rebuild it on Plymouth Hoe in homage to Smeaton's genius. And the secret of its success had been an innovative bonding material that could survive the constant pounding of the sea.
Smeaton experimented with mixtures of lime, clay, and iron slag to create hydraulic lime. I'm going to try to demonstrate the innovation that Smeaton accomplished at the tower. Here we have a traditional cob mortar. This is a mixture of sand and clay and straw and lime and a bit of earth. And these types of mortars were used traditionally for many hundreds and thousands of years. And the other material that I have here is Smeaton's mixture.
Smeaton's hydraulic lime is formed inside a cardboard tube before being placed in water, replicating the rigors of the sea.
And then I'm also going to do the same with the traditional earth mixture. Got both tubes now filled with the mortar. We're going to go away for about a half an hour, and then we're going to come back and hopefully we'll see a pretty dramatic difference in terms of how they've performed. First, we're going to look at the tube that's filled with the traditional mud mortar. We're going to see exactly how much it's set. And you can see absolutely nothing. This is the one we're much more interested in. This is the one with the mortar that's based on the hydraulic lime technology that Smeaton came up with. I can immediately feel that this one is much more solid. I squeeze it, nothing happens. If I have a look inside, I can actually see this now is very, very solid. That combination of setting very quickly and setting underwater completely revolutionized civil engineering. What Smeaton had created was the precursor to Portland cement. Portland cement's the key ingredient in all modern concrete.
The strength of Smeaton's hydraulic lime allowed engineers to dovetail together nearly 1,500 blocks of granite, creating a rock-solid structure that would stand up against the forces of nature. So solid, in fact, the Victorians found it too difficult to dismantle the base when it was finally relocated to Plymouth Hoe over 100 years ago.
So here we have the original 250-year-old granite blocks reassembled here on Plymouth Hoe with mortar, much like the original mortar. Incredible that it still looks so good. And if I look really carefully, way out there on the horizon, I can just see the base of Smeaton's original tower standing next to the new tower. This was really the game changer in concrete engineering worldwide.
At the Millau Viaduct, engineers enhanced Smeaton's groundbreaking formula to create a technically sophisticated form of modern concrete and used it on a gigantic scale, building 7 of the tallest bridge piers on Earth.
All the piers represent something like 90,000 cubic meter or more than 200,000 tons of concrete. And this is a concrete which is of a very high strength.
But for Chief Engineer Millau Viaduct to hit the 4-year deadline and avoid fines of up to $30,000 per day, each pier had to be built simultaneously at 7 individual work sites. And due to their extreme height and complex shape, radical engineering techniques were called for.
From here we can see the shapes of the piers. They look very simple, but it's very far from it.
Engineers broke ground in October 2001. Across the uneven valley floor, each pier had to be a different height. The tallest, a record-breaking 245 meters. Their octagonal shape tapers gradually, splitting 90 meters below deck height to provide greater flexibility.
It was necessary that the architect worked to make nice piers, but in the same time, it was necessary to select shapes which could be erected with self-climbing forms.
Built in 4-meter stages, engineers used a state-of-the-art self-climbing frame, a hydraulic-driven system that would push a giant reinforced concrete mold upwards.
One of the big problems, of course, was to lift concrete because this pier, this one, is 245 meter high.
Cranes were used to lift buckets of concrete, which was then poured into the concrete mold. After each pour was set, the mold was dismantled. The frame carrying the mold was then mechanically pushed by the hydraulic jacks up the piers and re-anchored in the set concrete. The mold was then reassembled, ready for the next pour. In total, each cycle took 3 days.
You can see the lines between the different lifts, concrete lifts, and also the traces of the elements where the climbing forms could be anchored to the concrete.
The piers were completed in just over 2 years, 1 month ahead of schedule.
Developing solutions to erect the 7 piers in the same time, it was a very, very, very big adventure.
But to complete the planet's tallest bridge on time, designers would again look to history's great innovators.
A vertigo-inducing 135 meters below me lies the Severn Bridge.
To create more impossible engineering. The Millau Viaduct in southwest France is an engineering wonder of the modern world.
When it was decided to place the structure to the west of Millau, then it was necessary to design a very big bridge to cross the valley.
Spanning the yawning abyss of the Tarn Valley, at 343 meters high, this supersized bridge stands taller than any other on Earth. But during its construction, its jaw-dropping height created a seemingly impossible challenge for chief engineer Millau Viaduct.
The great enemy of the design of the bridge is the wind. The deck is about 150 meters above the Plateau de France, and so this means that we have rather high winds.
So how do you construct a supersized bridge to cope with hurricane-force winds and turbulence on an unprecedented scale?
The solution is to reduce the wind force.
But diminishing the effects of the wind's tremendous power on the bridge deck would not have been possible without another ingenious innovation from the past. Professor Luke Bisbee is exploring one of Britain's most iconic bridges.
All right, now this is what I'm talking about. A vertigo-inducing 135 meters below me lies the Severn Bridge.
Opened in 1966 and spanning the River Severn between Ost and Chepstow, it was the first major road link between England and South Wales.
The main section of the bridge is over 1,598 meters long, which at the time made it the longest bridge in the world. I can actually see through this hole about 1,000 meters down the bridge. It's absolutely incredible.
But whilst the length of the bridge was an incredible engineering challenge in its day, it was the weather that posed the greatest problem of all. Lying inland from the Atlantic Ocean, the River Severn begins where the Bristol Channel ends. The high ground of Exmoor on the south shore and the mountains of Wales on the north create a funnel for the prevailing southwesterly winds and Atlantic storms, increasing their power.
Building a bridge that could withstand severe winds was really essential. And even on a relatively calm day, standing here underneath the bridge, you really get a sense of the wind that they were up against.
During the 1950s, pioneering British civil engineer Sir Gilbert Roberts was tasked with designing the longest windproof bridge on Earth. And the biggest challenge was the deck itself.
If you look at the shape of the deck, you can start to get a sense of what the solution was. And the most amazing thing is that the shape of this bridge deck and the solution they came up with was actually a happy mistake.
When testing the original truss lattice design in the wind tunnel, the model broke. Awaiting a replacement, engineers became inspired by other aerodynamic shapes, which led to a truly groundbreaking idea.
So what I have here is a model airplane, and you can imagine that the wing of this airplane is representing the bridge deck. So a wing has a curved surface on the top, and it has a flat surface on the bottom, and this means that air passing over the wing has to travel further across the top than on the bottom.
As air passes over the curved surface, it speeds up and loses pressure. The pressure of the air below remains high and pushes up towards the low-pressure area, creating lift.
What I'm going to attempt to show you is with this hairdryer to generate some wind, the force of the little model airplane will decrease, and that decrease will signify the lift force that we've generated on the model. So there we have our starting weight, 45 grams. Right, so there we go. The engineers here didn't want that to happen to the bridge deck.
However, if the experiment's repeated in reverse, the effect for the deck is beneficial.
What we should see is that this force should increase rather than decrease. You can actually see the downward force that's coming from the wind. That holds everything nice and taut and safe in very strong winds.
Now the curved surface is underneath, air loses pressure as it speeds up, and the high pressure above presses down.
And of course, this is exactly the principle that the engineers used on the Severn Bridge.
Sir Gilbert Roberts and his team created an aerodynamic steel box girder deck, the first of its kind in the world. Hollow and only 3 meters deep, with a cantilevered footway on each side, the deck is able to create a wind flow which holds it firmly in place. During its history, 13 vehicles crossing the bridge have blown over, but the bridge itself stays solid.
Although this beautiful bridge has passed on the burden of heavy traffic to its younger brother just downstream, it's still managed to carry more than 300 million vehicles since it was first constructed in 1966. And thanks to Sir Gilbert Roberts and his team, it's set to do so for many more years to come.
Engineers at the Millau Viaduct have advanced Sir Gilbert's inspired aerodynamic shape and created a cutting-edge bridge deck of their own. 1 kilometre longer than the Severn Bridge, at 2.5 kilometres and weighing a colossal 36,000 tonnes. It's one of the longest cable-stayed bridge decks on Earth.
The deck is streamlined. That means that it's rather shallow. It's 4.2 meters. And in addition, it has a continuous shape, very, very limited inclination, helps the wind passing below and reduces automatically the wind forces.
The deck is a shallow trapezoid shape, creating an inverse aerofoil to provide negative lift in strong winds. But building this colossal seamless aerodynamic steel deck in record time was an unprecedented challenge. So engineers decided to create a gigantic steel jigsaw puzzle, cut in dedicated factories across France and transported to Millau.
The central core, which could be spine of the bridge, has been assembled in a segment of 20 meters and brought with trucks to the site. The deck was assembled on the hills on each side.
2 work sites on each plateau were set up to receive the component deck parts. In all, 2,000 convoys loaded with cut steel travelled to Millau. The welding was completed in just 20 months, using a staggering 150 tons of welding material. But engineers at the viaduct were yet to face their greatest challenge.
One of the big questions was to launch the bridge from both sides of the valley. And it was not so simple to do that.
To span the huge chasm of the Tarn Valley, engineers would once again turn to the work of historic innovators.
All of these harness the properties of a revolutionary product. Wow, look at that.
To make the impossible possible. The Millau Viaduct in France's Massif Central is a work of engineering virtuosity. Taller than the Eiffel Tower, this bridge once seemed an impossible dream. Conceived by engineer Millau Viaduct, the project pushed the boundaries of construction.
It has been very difficult. The solution was not immediate. We had to work a long time to solve the problems, and it was a big challenge.
Perhaps the biggest problem to overcome was to place the 2.5-kilometre steel deck on top of the concrete piers. Their extreme height ruled out using a crane. The only option for engineers was to try to slide the 2 sections of deck from each side of the valley.
The piers are so slender that classical launching techniques would have been very critical. It would not have been possible.
The leading edge of the deck weighs 7,000 tons. The pier's great height-to-width ratio meant that they were susceptible to lateral forces. Pushing the deck across the pier's surface would create friction, increasing the lateral force, with potentially disastrous consequences. To solve this seemingly impossible challenge, Michel and his team at Millau would need to reduce friction throughout the launch process. A task that would not be possible without the ingenious engineers of the past. Friction has been a sticking point for man for thousands of years.
Heave-ho.
Ancient Egyptians, struggling to slide their building blocks across sand, realized water created a smoother, slipperier surface. Although too much was not advisable. It's thought the builders of Stonehenge rolled their giant slabs across a series of logs, which was the perfect solution, as long as the ground was flat.
Look out!
But luckily for engineers at Millau, a scientific mishap made in a US laboratory during the 1930s would provide a solution. Engineer Rhys Morgan is getting to grips with this accidental discovery that revolutionized the way we live.
Most people will recognize these day-to-day objects, but what most people don't know is that all of these harness the same properties of a revolutionary product called PTFE, or to give it its full name, polytetrafluoroethylene.
This groundbreaking product was mistakenly created by an American chemist, Roy Plunkett. In 1938, whilst developing non-toxic refrigerants, an experiment with a gas, tetrafluoroethylene, went awry. It unexpectedly solidified, coating the inside of the test tube with a waxy resin. Inadvertently, Plunkett had created what would become the world-renowned trademark, Teflon.
It has lots of different properties. It's very corrosion resistant. It's chemically inert. It doesn't react with other materials. And it has a very high melting temperature. But above all of these, it's very, very slippery.
And being slippery means it's very adept at overcoming the forces of friction. A phenomenon that is hard to deal with for a standard metal.
So here I have a sled connected to a metal tray underneath and about 45 kilos of bricks and sand. And as I pull the sled along, the tray is going to have a huge amount of friction against the metal sheet here. And that friction is retarding the motion. As I start to pull against this now, you can see I've got 5 kilograms and I've still got no movement. So that's the friction preventing my sled from moving. I'm up to 7 kilograms, 10 kilograms, 11, 12, and there it goes. So that's about 120 newtons of force to pull those along.
To see how PTFE performs, the metal tray is prepared. then sprayed with the slippery coating and cured at 430 degrees Fahrenheit.
Wow, look at that. That looks incredibly smooth. So let's give it a go. I've got 2 kilograms, 5, 6, 7, and look, it's starting to move already. 7 kilograms here to overcome the friction. And you compare that to 12 kilograms, that's 120 newtons. So that's about 50 newtons difference to move the same amount of weight.
PTFE is made solely of carbon and fluorine atoms. Fluorine has the highest electronegativity of any element, repelling all other atoms. The fluorine wraps around the carbon, so it's unable to react to anything. As a substance, it is therefore highly unreactive and creates almost zero friction. The sledge can carry up to 40% more weight when pulled across the PTFE-coated sheet, the equivalent of a 5'9" engineer.
How much are we seeing?
Wow.
There you go, 12 kilograms, 120 newtons. How about that?
Engineers at the Millau Viaduct took PTFE and incorporated it in a unique mechanism that would conquer the launching problem once and for all.
It was necessary to create a system where the launching force was created pier by pier in such a way that no force, no bending was produced in the piers.
To do this, the team created a translator, a machine that uses the slipperiness of PTFE and hydraulic jacks to lift the deck off each pier entirely before moving it forward.
At this point, we have one of the equipment which has been used to launch the bridge. On each support, we had 4 of these machines.
Each translator uses 2 wedge-shaped blocks coated in PTFE. A hydraulic ram pulls the upper wedge, which slides it up the lower wedge. This lifts the deck away from the pier, pushing it forward at the same time. The lower wedge then slides backwards, lowering the deck back onto the pier. Each cycle moves the deck 600 millimeters.
All the launching systems are moving in the same time by the same distance, and so you can understand very clearly that it's not producing any force in the piers.
But before engineers could begin the launch, there was another problem.
The typical spans are 342 meters long, but it's much too long to be crossed directly. So it was necessary to install in each span a temporary support, a big truss, in order to divide the span by 2.
7 temporary piers were built across the valley, and in February 2003, the launch began. But as the 2.5-kilometer deck was pushed out into the void, the course was not straightforward.
Here, from the north abutment, we can first see the curve of the bridge. The bridge is curved with a radius of 20 kilometers, which is very, very large.
As the 2 colossal sections progressed their curved course from opposite sides of the valley, engineers had to rely on GPS technology to ensure pinpoint accuracy. And in May 2004, 15 months after they were first launched, the 2 sections of deck finally met above the Tarn River. And incredibly, they were only out by a few millimeters.
This system was really the key of the success.
But to complete this audacious bridge, the team at Millau would once more need inspiration from the great innovators of the past.
Today, the bridge is considered a real landmark breakthrough in the world of engineering.
To create more impossible engineering. Connecting the high plateaus of France's Tarn Valley is the Millau Viaduct. This audacious road bridge is the country's tallest structure and is one of the greatest engineering achievements of all time. Conceived by engineer Millau Viaduct and designed by architect Norman Foster, environmental considerations were key.
The first thing to do was to preserve the quality of the site because it's a beautiful site.
The unstable limestone ruled out a suspension bridge, which relies on firm anchor points at each end to take the weight of the deck. For Millau Viaduct, there was only one solution.
I wanted to design a cable-stayed bridge because cables are very strong. They allow to make very, very modern structures, very light and transparent. So it was, from the beginning, I wanted to make a cable-stayed bridge with multiple spans.
Constructing a multi-span, cable-stayed bridge on such a huge scale in a hostile environment was considered an impossible challenge. One that could not have been overcome without the ingenious engineers of the past. Structural engineer Jonathan Ledin is paddling the great Strömsvatudal in Sweden, searching for the source of an historic engineering breakthrough.
For centuries, this stretch of river here in Strömsund has been an obstacle that travelers needed to overcome.
As cars became more commonplace by the early 1950s, it was decided a suspension bridge would be built. However, German engineer Franz Dissinger, who won the commission, proposed a different idea. A key player in rebuilding Europe post-World War II, where 15,000 bridges were destroyed, Dissinger's construction solutions were cost-effective and efficient.
What Dissinger built was this, the Strömsund Bridge. A cable-stayed design that has since been recognized as a landmark in engineering history.
After carrying vehicles for over 60 years, the supporting cable stays are being replaced for the first time. And it was Dissinger's approach to installing these cable stays all those years ago that was to prove so influential. The way a cable-stayed system works is simple, yet very effective.
Imagine my arms are cantilevering out from my body like this, and I'm trying to hold the buckets of water in place like this. I need to do a lot of work with my arms. This is not exactly easy to hold on to. I'm going to use this rope here to represent the stay cables attached to the bridge deck. And I'm going to pull that over my head, which is representing the piers. So now the majority of the weight is no longer carried by my arms, but through the cables onto my head and down to the ground. And that is exactly what is going on behind us. The weight from the bridge and the loads from traffic are being transferred through the cables and down onto the piers.
Early cable-stayed bridges, however, were structurally weak. Rudimentary cables and limited understanding of the forces at play in the system meant by the early 19th century, the idea was all but abandoned.
And the problem that the engineers were struggling with in the past was designing the cables so the loads would be distributed evenly among them. The consequences of one or more cables being overtensioned could potentially be disastrous.
To overcome this problem, Dissinger looked to mathematics. He created formulas to calculate the forces required of each cable. Each of those cables was then precisely tensioned on site, and engineering first. Now they're being renewed using exactly the same process.
So these are the brand new cables that are going to be installed overnight. And just as would have happened all those years ago, they're first going to be mounted in place and then precisely tensioned. Dissinger's innovative approach makes this possible to do in just a few hours.
Dissinger's pioneering construction technique has influenced some of the most iconic bridges around the world.
So the work has been going on here on site all night. And what's remarkable is the way in which all of this is being done is really not that different from what would have taken place here all those years ago. So today, the Strömsund Bridge is considered the first true modern cable-stayed bridge and the real landmark breakthrough in the world of engineering.
Engineers at Millau have taken Dissinger's methods and magnified them, and created a structural masterpiece.
The originality of this bridge is that it is a cable-stayed bridge, but with multiple spans. This is really very special.
Whereas the Strömsund Bridge has only one central span, the Millau has 6. So as the 700-ton pylons were erected, engineers had to trust they'd calculated the perfect distribution of rigidity and flexibility throughout the structure. Key to its success lay with the cable stays themselves.
So this is one of the stay cables of this bridge, which procures the necessary resistance. In fact, for each of the 7 pylons, we have 11 stay cables on each side, so 22 per tower.
The strongest cables are made of 91 steel strands and have the breaking strength of 2,000 tons.
These cables are more resistant than ordinary steel, and this is why stay cables are extremely efficient to design very long spans.
They're so strong, engineers installed just a single axis, and only when tensioned did the entire bridge become rigid. After little more than 3 years of construction, the integrity of the bridge could now be tested. 28 trucks, weighing a total of 900 tons, were driven en masse to the center. The deck flexed, but only a few centimeters, and the bridge remained firm.
Today, I'm of course extremely proud because there are many steps in erecting a bridge like this. Finally, when the bridge was completed, it was an enormous success.
Opened in December 2004 and finished 2 months ahead of schedule. The Millau Viaduct marks a significant milestone in bridge engineering. Now used by nearly 5 million vehicles each year, for engineer Millau Viaduct, it represents the achievement of a lifetime.
You know, when you have passed years working and fighting for a bridge, you know, and that suddenly it's finished, there is really a moment where you don't know what to do.
By learning from the great pioneers of the past, adapting, upscaling, and making innovations of their own, engineers and designers succeeded in making the impossible possible.
Many thought that it would be impossible to build that bridge, and now it is there.